Waqas and I'm a PhD student of electrical engineering at the Missouri University of Science and Technology. And the topic of my presentation is sizing energy storage system for energy arbitrage in extreme fast charging stations. Integration of the energy storage system with extreme fast charging stations can be useful in many different ways, but the most important applications are power buffering and energy buffering. In energy buffering, the ESS can be used to store the energy during off-peak prices and discharge that energy during the peak prices and earn revenue during this process. So, therefore, it is important to optimize the sizing of the storage system and obtain the optimal energy management scheduling of the charging station for minimization of the operation cost and the investment cost while satisfying the performance requirements of the station. In this regard, a novel nonlinear programming model is proposed, which is implemented and solved in the AIMS software. The important features of the proposed model are shown on the right-hand side. The proposed model aims to obtain the optimal energy and power rating of the storage system and the optimal energy management of the charging station by considering the reduction of the total demand charges. Total demand charges consist of two components. One is the monthly demand charge, and the second is the annual demand charge. And this particular formulation is based on the realistic utility practices. Moreover, the proposed model uses an improved ESS life degradation modeling based on polynomial curve fitting. And the proposed model uses a cumulative charging and discharging energy-based cycle counting method. The objective function of the nonlinear model mainly consists of three components. The first one is the reduction of total demand charges. Second component is the reduction of investment cost components, and the third part is the reduction of operational cost component. The investment cost component of the storage system are annualized using the ACF factor shown at the bottom of the slide by considering the interest rate of 4% and the lifetime of 10 years. This lifetime is basically the project lifetime. The results of the proposed model are shown in this slide, where figure 1 shows the input data, and which is consists of the charging station demand and the electricity price curve. And figure 2 presents the optimal energy management scheduling of the charging station, where we can see that the energy storage system charges during the off-peak prices, and it mainly discharges during the peak prices, which also coincide with the peak demand hours. So this way it can earn the energy arbitrage savings. And we can also see that the storage system also discharges during during these intervals. And this is mainly to ensure that the average power imported from the grid is minimized. So in summary, the proposed model results in annualized savings in the total cost of about 6%, and optimal depth of discharge and the annual cycles of 92% and 346 cycles per year. And we also did another study in which we studied the effect of degradation modeling, and we've observed that ESS will reach to its end of life after about 7 years if the degradation modeling is not considered. So it will need to be replaced, which will incur extra investment cost. And lastly, we've seen that the proposed model results in a reduction of maximum average power import from the grid by about 26%. And some sensitivity analyses were performed to gain the insight how different parameters result the ESS sizing and savings in the total cost. And in the sensitivity analysis, the sensitivity of ESS sizing and saving is analyzed with the allowed annual ESS cycles, the electricity price multiplication factor, and the ESS investment cost multiplication factor. And we have observed that there's a trade-off between the investing in the ESS and the arbitrage savings. And figure 7 presents the sensitivity analysis of ESS and the savings by simultaneously changing the values of EPMF and EIMF. And we can see that for the region with lower EPMF and higher EIMF, the deployment of ESS is infeasible, and it doesn't result in any savings. So in conclusion, the degradation of the ESS modeling is extremely important. And as a future work, the application of the renewable resources and the uncertainty in the input data and linearization of the nonlinear programming model can be attempted. Thank you.